Hi, my name is Konrad Krawczyk, and today in the Computational Antibody Protocol series, I'm going to talk about a topic that might appear tangential at first, which is the entire dataset ecosystem for antibody discovery. So it might seem tangential, but actually, if you think of it, for any kind of model, like you do need a dataset. So it becomes very fundamental. So I'm going to cover what is the role of public data sets, why do we put a lot of effort into organizing them, and where I think that the field and all of the computer analyses like should go forward, which is the dataset generation. But first of all, let's have a look at like what would different kind of people in the antibody analyses pipeline how they would use a data set. So it very much depends on what kind of hat do you wear at any given point. So a machine learning engineer might see a data set only as a means towards training their model. If you're more towards the legal or business development end, then perhaps a data set is just a way of looking whether there was a prior art so that you can patent your candidates. If you are a biologist, then you might look for data in papers if you or in a data sets where you find sequences that you can mutate further or just use as inputs for your library design, yeah, to have binders toward the same target. So one bit that I think that is quite overlooked sometimes is that actually looking at the data actually gives you fundamental understanding of the data itself. Yeah. So it is actually like one of the least glorious bits of any kind of data analysis, like whichever of the above mentioned tracks you want to use. But actually getting data in a single place, analyzing it, trying to figure out like what kind of model, like what kind of search function you want from it is giving you a huge understanding of the underlying data. Yeah. Which is actually very, very important in our field, in biology. And I'm going to address it at the very end about when I'm talking about data set generation. So why do we actually go towards this kind of, organization of the data? Well, it touches upon like in several topics. So firstly, you do want to have your data organized because you want to do search, you want to train the models, but you also want the understanding of it. Yeah. And there is a lot of data in the public domain, but there is also a lot of data and silos within corporations. So when you actually like you do this exercise, let's say like in one company or on the public data sets as we do, then it gives you or us at this stage an understanding of like how you can replicate this effort anywhere else. So in if I can use the example of the public data, then everything is actually like half organized. Yeah, it is a bit of a half organized mess because in many cases the repositories were not designed to be used for machine learning. Yeah, like if this is your target use. Yeah, but neither were they for search. So repositories such as PDB are great for structural predictions, but they do not exactly talk to other repositories such as clinical data. Yeah. So one part of it, and it is an activity that can be replicated across, data sets, organizations, and so on, is that you look at this half-organized mess and you find a common denominator. So in our case, which is the public data, you look at the antibody sequence, yeah, because this is from something that you can identify from a large body of sequences. So this entire step is not trivial. It requires quite a lot of compute, and it's by no means the last one. Yeah. So actually going from here to here can be done somewhat automatically. Yeah. If you have a large set of sequences, then you can have a model that tells you protein sequence or generic protein sequence and antibody sequence. But going from this set of antibody data towards something that is cleaned and can be used either for search or for model training requires much more tinkering and in many cases just manual curation. Yeah. So where does this actually bring us in terms of building the understanding of the data? Yeah. So if you are looking at antibody data set, yeah, or even like any protein data set at that, yeah, like then whether it's in the public domain or within the organization, then you would like the ideal scenario to be that your coverage of targets is very uniform so that you can develop a binding model that is generalizable, and your coverage of different properties such as binding developability and formats is also quite uniform. Yeah, so we know that this is an idealistic scenario. And on the example of public domain, but also some organizations, like, we know that actually the picture is much more patchy. Yeah. So in terms of targets, like, in the public domain, we have a very skewed coverage, yeah, which is not that surprising, yeah. So like even if you think of what would happen in a big organization, you do not exactly focus on covering all of the proteins in your proteome to actually develop binders, but you would focus on a much smaller set that are therapeutically relevant. In terms of properties, there is an overrepresentation of certain data types in the public domain. So for instance, positive data points for binding are out there, but the negative data points or developability is very scarce. So the reality is that you actually can get all of those, so like pockets of resistance, like where you might get a lot of data, but you get gaping holes in other places, yeah? And those are the spaces that need to be either inferred from existing data sets, which is not that easy, or simply covered by generating more, yeah? The point is that without actually going through such an exercise of actually mapping the data space, you actually don't know where to go next, yeah? Unless you have a very big budget and you can just, shoot blind. So here I'm going to talk about how, I see it, yeah. And mostly I see public data as very horizontal, with generated data as your way of getting the vertical coverage. So if you look at the bottom here, I see different types of data sets, yeah, and this is what I call horizontal. So you get the NGS, you get structures, developability, data points, different formats. So public data is a very good way of covering very, a very horizontal space, but in a very uneven manner. So NGS sequences, we have a lot of structures, we have far less. Certain formats we do not even have any data points for. Yeah. So actually, in knowing where you have a lot of data, where you have not that much data, and in the process developing models to try to squeeze something out of those data sets allows you to see where you should focus on efforts to actually generate more data points. Yeah. So we have done this exercise for the public data, and right now you can access it on the link below. And it does reveal that there is quite a lot of discrepancy between the sizes of the data sets, how they are covering the space or not. And that's why we started generating our own data sets anyway, now that we know where those patches and coverage are. However, I'm going to cover the data sets that we have developed publicly because they are available on our website. And I'm going to, do something facetious, yeah, which is, I'm going to say how you could get those data sets using, let's say, a pretty nice tool, which is ChatGPT, yeah. And this is designed to show you what would you get using public sources versus why did we actually put the effort in, yeah? Because this is always the question that we get, why would you re-download and regenerate something that is available publicly? Yeah, in most cases, because you do need it cleaned up. So each one of those data sets actually merits a paper, a video on its own. So I am going to go through them in let's say in quite a superficial manner, but to give you enough information as to what it is, what is the application, where you can get it, and why did we actually bother redesigning it. So first one, of course, structures. You can use it for structural modeling or co-folding, which is facets of the same thing, such as an AlphaFold. And if you want to just get it, you go to the source of all structures, which is the PDB. But right now with the AlphaFold DB, you also have a lot of outlet into where you get model structures. Of course, if you want to be antibody specific, you go to resources such as SABDAB, and as of last years, and there are many clones of those resources. So why did we actually put in the effort into redoing quite a lot that tools such as PDB and SABDAB offer? Well, mostly because anyone that ever dealt with a PDB structure knows that you not just take those structures and you can run the predictor, and they need to be cleaned for missing residues, for different numbering schemes, and for certain analyses, such as distance analyses, you actually need to calculate them in a normalized way. So there is quite a lot of calculations that go into our structural data set that we make available, and I hope that everyone is going to find them useful as well, mostly to save the effort. Then we have the NGS sequences. So that's a data set. It's a massive data set that allows one efforts such as language model training. But if you only want to use it as a data set, you can search through it for viable scaffolds. So if you want to just grab this data set for proteins, you get the UniProt, and for the antibody data sets, which are the unpaired and paired ones, you get the observed antibody space and the iReceptor. So again, why did we actually bother to reinvent the wheel here? Well, firstly, if you are dealing with sequencing data, it is beneficial to be able to do it conscientiously so that you know which data sets you have enough data to actually be able to call what is an actual read and what is bogus. And in doing so, you can perform manual curation to see which data sets are actually one disease and which organism they coming from. Yeah, because the annotations in CBI might not be as clean as you would like them to be. Finally, if you are doing it on and on and on, then you can go a much more larger scale, especially if you automate the process to an extent. Next, we have the patents. So this data set can be used as a very cheap prior art check, yeah, without legal liability from us. So you can also use it to see what sequences other people developed, yeah, around some primary sequence, and so you can make the library out of that. So there are other applications here, but one that I always say is that patents is it is a data set that is quite messy because it's not designed to convey information, but legal protection. Yeah, so you are not guaranteed that all the sequences that are in the patents are actually going to work. So where you can get it in 5 minutes, obviously from GenBank, because they have subsets of patented sequences, PlabDab if you want an antibody-specific version of it, and there are some other resources. So why did we actually put in the hours? Well, firstly, because we wanted to go beyond just GenBank, yeah, because we noticed that there are many sequences that are in the original sources, like USPTO full text search, but they are not in GenBank. Yeah, so we had to go to a lot of original sources to actually get the large scale coverage that we have right now. Then we have the annotation part. So if you do it in half agentic, half manual way, then you get, let's say, a never perfect because it's patents, but a better annotation for targets, yeah, which can then feed into your applications of either library design or prior art check. Then we get to therapeutics. So this is a very useful data set for looking at what actually works, what goes through all the hoops in terms of clinical trials and developability checks. If you want to get this data set very fast, so WHO publishes the INN lists with sequences, so you can just grab this data as they come out. But if you want them already annotated for antibody information, you can go to TheraSabDub or IMGT. So again, here, if this data is so easy to get, like, and why did we put in the hours? Well, mostly because to actually get the annotations for clinical stuff, you need to put in a lot of effort. So this data is half organized, but requires quite a lot of annotation and cleaning to actually get proper data points out of it. Yeah, so if you want any kind of PK/PD immunogenicity, you really need to do this half agentic, half manual curation to get a data set that you can actually get some proper information out of. Finally, we get the antibody antigen pairs, which we lovingly refer to as papers. This is the only data set that I would say that we do not know where the end is. Yeah. So like for most of the others that I said, we know the set of sequences where we need to identify the antibodies out of. Yeah. In papers, this is not the case, yeah, because even though I can get a predictor at this stage that tells me whether there are some antibodies in there, it's a very far cry from actually being able to say whether there are useful antibodies in there. So perhaps like we're going to get there to actually get a predictor that is going to tell us like what is the proportion of papers that has useful antibody antigen pairs. But for now, this is covered by half automated way and half manual curation. And there are multiple resources like that you can get. So you have a Scampi and ABDB that have created different data points. You have Abigem, and there are many data sets that are coming out that cover different facets of it. Yeah. So why we again like put in the effort, even though like there are public resources like that, is that we wanted to start scaling it so that when we developed our data model that covers structures, patterns, papers, so that we could actually be adding new data sets and be able to control how does the model perform and scale as we add more data in there. Yeah, because those data sets are very heterogeneous. Yeah, like one can be structural for a few targets, like one can be just a single target data set that has sequencing data associated with. Yeah. So this pretty much covers the public data sets. So like we have heterogeneous sources, we have some patchy coverage of certain data types such as structures. We have a lot of sequences. We don't have many developability data points. In terms of binding, we have a lot of positive points, but many negative ones. So if we want to start covering those holes, we need to be strategic about like where we are going to start doing that. Yeah. And it is not as easy as, we have a few structures, so we just generate some more. We have not that many negative data points, then we'll generate some more. And why this is not that easy, I am going to talk about some of the issues within the data generation. Yeah. But before we actually do that, we should talk about what is the actual objective for generating more data. It's not actually the search bit. So obviously it's generating data for machine learning. So for that, we need to firstly define what is the objective in terms of generating data so that the models can, let's say, like can get off the ground. For us, this is addressing the optimization problem. So when you get the initial sequence, you want to mutate it in such a way that you improve its affinity and developability properties. This is a solved problem pretty much in experimental terms. So if you have an ample budget, you know your lead quite well, then you can pretty much define a sequence that is going to tick all the boxes. Yeah. Doing this in computational terms is much more difficult. Yeah. And it is increasingly difficult depending on what kind of input you get. If it's just one sequence, if it's a set of sequences that target a given target, or if you start from a crystal structure, then it is so much easier. So keeping in mind that this is where we would like to start generating data for. Let's talk about two, let's say, like perception issues that are also associated with data generation in biology, but that need to be addressed. First one is the scale of the data that needs to be generated and its cost. So right now, like when you're looking at all the great models in image analyses and video generation, text, and so on, remember that those data sets are very, very, very big, and individual data points are very cheap to get. Yeah. So an example, text to image data set that this weird image on the left was generated by was trained on hundreds of millions of text image pairs. Yeah. And you know, as a human, like you can generate a text image pair right away. In terms of structure prediction, so sequence structure pairs, we are operating on roughly 200,000 structures on the PDB, and this is not even the non-redundant set. Yeah. And it is actually quite a long ask for a human to, generate a structure just, seeing the sequence. Yeah. I know that like I would be able to more or less draw an antibody when I see the sequence of it, but not to the point that it would actually make physical sense. So, and every single point like that, structural is an extreme case because it costs an arm and a leg. But even getting individual productions for, say, like in developability or like binding, this costs a lot. Yeah. So that's why actually being strategic in terms of like, what data you generate is actually very, very important because, every point costs a lot. So it better be worth it. The other bit here is the perception. So we are expecting of the biological models to answer questions that we do not know the answers to. Yeah, this is quite facetious that like the way that I'm putting it, but imagine the issue of either what GPT does, so generating text, or doing the text to image as a human. So with the silly example of image of a giraffe with dragon wings, I'm pretty sure that you would be able to produce something that fits this model. But in similar terms, for the structure of an antibody antigen complex, if I asked you to replace the red residue with something that would maintain the structure or even better, make it bind better, then even if you have a lot of experience as a crystallographer, I'm pretty sure that you will struggle with the task, or at least like you will not be able to do it 100% time accurate. So do keep in mind those 2 points, that we are in need of generating data sets that are very expensive, where every data point needs to count, and that we cannot actually know as humans like what the actual answer to the problem is. Yeah, so like these are 2 very big problems. One way that we are addressing it using data generation is, for instance, using the app design dataset. So this dataset is used for estimating on single structures of antibody antigen complexes, like if you make a mutation, is it going to break up the complex or not? So a much better way of doing it would be using SPR affinity maturation affinity measure, but we had a budget for ELISA. So here we generated a set of mutants from a set of antibody antigen structures. And we did it in a way that is not only alanine scanning, which is quite prevalent in existing data sets, but we have done it in a more directed way so that you get like a much better coverage of the mutations. Of course, like there are data sets like that in the public domain, such as Scampier ADDB, that annotate structural data points with affinity ones, but because they are very much skewed towards alanine mutations, machine learning algorithms struggle on them quite a bit. So one bit that I'm trying to demonstrate here is that when you generate data sets, see like how many birds with one stone I actually got here. So this is a pseudo-structural data set. because I am starting from an existing structure, and because I cannot allow myself to recrystallize all of the structures, I'm only doing point mutants. Because I am making quite comprehensive coverage of all the single point mutations, then I'm actually getting negative data points as well. Then towards the very nebulous question of, that like I would like to train the model on something that I do not know the answer to, doing point mutants where I actually know the controlled environment of the structure, and trying to ask like in what mutation would work and what wouldn't, is actually providing data points that might allow us as humans actually like gain more understanding into actually what is going on. Yeah. Rather than going gung-ho and defining a data set with a lot of point mutants, throwing it in the black box, and we actually don't know how it works, so long as it produces some answers. Yeah. So any kind of data generation that we are attempting right now is very strategic in terms of covering many bases and allowing us to learn not only like how to train a model, but to also be able to reason about the answers that we are getting out of them. Yeah, and this is pretty much the direction that we're taking with our dataset generation. And there will be more datasets coming soon. So to conclude, where do you actually get to all this data? So all of the public data sets that I have mentioned that are from other academic labs, then obviously you just go through the presentation and you can find them. For our data sets, so like everything in one spot, if you want to use them for machine learning, then if you follow the link, naturalantibody.com antibody data, then you'll get there to the papers and to the data sets. If you are more towards data search, then you go to the open.naturalantibody.com, you create an account, log in, and you'll be able to search through our data sets of patents, therapeutic structures, and some more. Yeah. I need to say that the search data set is actually a subset of all the data sets that we have, because not all of them are suitable for search, and not all of them would actually be useful for search. Thank you very much. I hope that this was very informative.